Hello students. Thursday night, which means tomorrow's Friday, which means that after that's the weekend. Fortunately, we do have a quiz tomorrow, which I'm sure that everybody's at home studying for. It's only a 3-problem quiz, not too terribly difficult, and there's nothing on the quiz that's not on the homework. So anyway, the video I made, the writing was really blurry, which I do apologize for. So I want to do this one and make it pretty much about the same, maybe just a few differences. I'll go through a level surface with friction, a level surface with friction, non-parallel applied force, and a ramp with friction as well. Okay, the level surface. So let's say there's this box and a ramp. Typical situation. Happens every day. And there's a guy pushing on the box with an applied force. And let's say in this example that the applied force is actually given. Let's say we get a decent amount. And let's say the mass of the box is 40 kilograms. And what we want to do is to find mu of k. And that means that the box must have some sort of a velocity or motion to it in order for the coefficient of friction to be kinetic, mu of k. So I'm going to draw my forces. Force due to gravity going down. Normal force going up. The guy is pushing on the box with an applied force, F of A, and therefore the box has some sort of a resistance, force of friction. So I'm going to do some of the forces in the y direction first. Some of you are asking me why I do that, and the reason is because I need to get an equation for the normal force. So forces in the y direction is equal to a negative force due to gravity, a positive normal force, and that's equal to 0. So when I solve for the normal force, I get N equals the force due to gravity, and the force due to gravity is the mass multiplied by 9.81, or little g. Hopefully the lighting's a little better on this. Hope you guys can see that. And then I'm going to do some of the forces in the x direction over here. F of x. Oops, I'm sorry. Some of the forces, I didn't put the sum sign, or as some of you guys say, the sideways m. Some of the forces in the x direction is let's say this is negative and positive. Negative force applied plus the force of friction equals 0. I want to have one of those on one side and the other force on the other. So I'll put force of friction, I'll leave it on the left. Move the applied force to the right. I get that way both of them are positive. The frictional force, we know what that is. It's mu multiplied by the normal force. Just in case you forgot, the force of friction is mu N, where N is the normal force. And so therefore my frictional force is mu. The normal force is mg, so mu mg is equal to the applied force. And I'm solving for mu, so I'm going to get mu equals the applied force divided by mg, which is, I guess I could write numbers here, 700 divided by 40 multiplied by 9.81. Should get 1.78. It's a decent amount of friction. 1.78 for my coefficient of friction. And it's a coefficient, so it doesn't have any units to go along with it. Rock and roll. And if I had been asked for the applied force, obviously I would have already been given the mu. So a lot of you guys are asking, how do you know whether or not what you're solving for? Well, one thing you can know what you're solving for is it'll say what you're trying to solve for. But also, if you're solving for mu, then that means you must have a lot of other information, like probably the applied force. Or if you're solving for the applied force, then you probably have information such as mu. Alright, the other one I was going to do, level surface with a non-parallel applied force. Oh good, that one only took 5.5 minutes. So here's a level surface. I'll make this picture kind of good size, so hopefully that makes it a little more clear. Big mass M, and let's say that it's being pulled by, I'll just make it the same. Being pulled by a person. These stick figures, constantly stick figures. He's holding up this string going down to the mass, and that with the horizontal makes an angle theta right there. So there's our image of the guy pulling on the mass, and let's use the same numbers, well, some of them. We'll say this mass is also 40 kilograms, and let's say this mu is 1.75, just like on the previous problem where we got, 1.78. So the mass is 40, the mu is 1.75, or I'm sorry, 78. Sorry, my bad. And we're curious what's going to be the applied force necessary. Well, before, the applied force necessary was 700 newtons when it was parallel. Do you think this is going to be 700 newtons of applied force when he's also pulling up on the object? There's the F of A force. I'm drawing my diagram. Normal force. Force due to gravity. And the frictional force opposing his motion. There we go. Okay, all the actual forces have been drawn. Now I'm going to write on here. Here's the applied force going in the x direction. And here's the applied force, or F of A, going in the y direction. And for a non-parallel force being applied, we all remember, I'm sure, that F of A, F of A in the y direction is the applied force multiplied by the sine, and the applied force in the x direction is equal to the applied force multiplied by the cosine theta. Excellent. Got everything set up here. Now I'm going to start making some force equations. Sum of the forces in the y direction is equal to the normal force going up, positive, plus force applied in the y direction is going up, and minus force due to gravity going down. All this equals 0. Now some of you may be wondering, how do you know what to do with this? Well, I know from experience and from doing my homework that I'm eventually going to have a frictional force on some of my forces in the x direction. And I know that frictional force is going to have a normal force in it. And so therefore I need to get an equation for the normal force. So I get N equals force due to gravity added to the other side, moved over, minus force applied in the y direction, F of A in the y direction. That is my equation for the normal force, and if I want to substitute in the equations for each of those, mg is the force due to gravity. The force applied in the y direction, there it is, F of A sine theta, so minus F of A sine theta. Okay. So that gives me an equation for normal force. Okay. Might run out of room on this one a little bit. Move that paper down a bit. There we go. Okay, now I'm going to do the sum of forces in the x direction. Sum of the forces in the x direction is equal to, there's a negative frictional force going to the left. I have positive applied force going to the right. So I'm going to put F of A in the x direction minus the frictional force. Looks like there's no other forces in the horizontal direction, so that's equal to 0. And when I solve for the applied force, I'm going to put in the equation for this one, f of a cosine theta equals, I'm going to move the frictional force to the other side, mu multiplied by n. This is my frictional force. I simply moved it over to the other side, and we know that n is all of this, so we can say that right there is equal to mu multiplied by mg minus the applied force multiplied by sine theta parentheses. So basically I moved this one over to this side, and the frictional force is mu multiplied by n, and I know that n is all of this stuff right here, so I simply make a substitution, mu multiplied by n. There we go. So I can kind of disregard this stuff right here in the middle and say that the applied force multiplied by a cosine of the angle is equal to mu multiplied by mg minus f of a sine theta. Okay, no more substitutions to make. Now we're just going to move around a few things to get f of a by itself. I'm going to distribute this stuff on the right hand side. I'm going to distribute it, so I get mu mg minus f of a mu sine theta Oh, by the way, I'm sorry, this is a moving problem, so that's mu of k. I should have said that. Where is it? There it is. Mu of k, mu of k, mu of k. There we go. Okay. Now I'm going to bring this one over to this side, so I have the two applied forces terms on the left-hand side, f of a cosine theta plus this one. Oops, I forgot the mu, sorry. There we go. And this is equal to everything that's left right here, mu of k mg. There we go. Now I'm just going to factor out the video. Oh boy. Hope the video's good. Video's still going? Okay, good. Now I'm going to, I'm sorry, I'm going to factor out f of a multiplied by cosine theta plus mu of k sine theta equals mu of k mg, and therefore I'm going to divide by all of this stuff right here into there, so I get mu of k mg divided by all of this cosine theta plus mu of k, oops, oh my goodness, sine theta. There we go. Okay, so this is what I had, f of a cosine theta plus mu of k sine theta equals mu of k mg. That's divided by all of this, and that's what gave me this equation. Now I'm going to plug in the numbers. Oh no, I think the video just froze. Oh my goodness, I'm going to kill this machine. Oh boy. Let's see if it's still working. Well, while I'm trying to get the computer to work, I hope you guys at home are plugging in numbers. I don't know, it looks like the video is working. I'm going to assume that it is, because I don't have to make it again. So when I plug in numbers, here comes the numbers. Okay, I wonder if this applied force is going to be more than or less than the applied force on the previous problem. 1.75 times 40 times 9.81 on top, divided by parentheses, cosine of the angle. Where's the angle? Oh my goodness, I didn't give you guys an angle. Can't be plugging in numbers without an angle. Let's use 25 degrees. It's a nice number. Fascinating. 414 newtons. That is significantly less than the one we had on the previous one where I used an applied force of 700, and it was the exact same mass. I'll show you guys one more time. An applied force of 700 newtons to move the exact same mass, but the force was applied in a parallel direction. Now the force is applied at a little bit of an angle, and that means not as much force is needed to move the mass. How neat is that? Okay, one more. This one, I'm going to make another ramp. And for this one, let's just put a mass right here on this ramp. Let's make this one maybe partly similar to the lab we did today. That would be pretty neat. There's our angle theta. I'm going to draw a set of force diagrams here. Or sorry, the forces on the object. So there's force due to gravity going down, normal force going up. Oh yes, and we're going to say, sorry I didn't say that the velocity is constant going down the ramp, so we have a constant velocity going this way, force of friction going up the ramp, because it has to oppose the velocity. And what do you guys want to solve for on this one? How about solving for, let's solve for mu. Okay, and we'll use similar masses here. M equals 40. Let's say theta equals 25 degrees in kilograms. Okay, I'm going to set up. I'm going to set up a sum of forces in the y direction first because I need to isolate the normal force. Sum of forces y direction equals, oh my goodness, I'm so sorry, I totally forgot to draw the pieces. Here's the force due to gravity going down the y direction, and here's the force due to gravity F of g in the x direction. Okay, now I can set up some of my forces. So some of the forces in the y direction, I have a positive normal force going up and a negative force due to gravity in the y direction going down, and that's equal to 0. That means the normal force is equal to the force due to gravity in the y direction. And as we remember, just like it was yesterday, which it was, force due to gravity in the y direction is equal to mg sine, oops, I'm sorry, that's a cosine theta, and the force due to gravity in the x direction is equal to mg sine theta. Okay, so that means this one, normal force is equal to f of g in the y direction, so that's mg cosine theta. Okay, that gives me my normal force. Now I'm going to do the same thing for the forces in the x direction. Sum of the forces in the x direction is equal to, there's no applied force here on this one, it's just an object going down a ramp with a constant velocity. And so I have going up the ramp as a positive force of friction, going down the ramp as the negative force due to gravity in the x direction, equal to 0. That means the frictional force is equal to force due to gravity in the x direction. Therefore the frictional force, oh I'm sorry, I should make the substitution for each one. Frictional force, we know that's mu times n. Mu multiplied by n is equal to, the equation for f of g in the x direction is mg sine theta. Now I'm going to substitute the equation for n, and I get mu multiplied by n is mg cosine theta, so mu multiplied by mg cosine theta is equal to mg sine theta. mg sine theta. Let me just show one more time how I got all those. force due to friction is mu multiplied by the normal force, and the normal force, we already determined that to be mg cosine theta, so I make the substitution right there. And then here's force due to gravity in the x direction coming down. I'm solving for mu, so I get mu is equal to, I'm going to divide by all of this over to here, mg sine theta divided by mg cosine theta. Oops, there we go, theta. Look at all the things that cancel out. Isn't that wonderful? Cancel, 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 cancel. And we get sine theta over cosine theta. I wonder what this will give me. 25 degrees, sine 25 divided by cosine 25. Look at that, 0.466. Mu equals 0.466. Pretty neat that when I use the same mass as the first problem, here's the first problem, mass is 40 kilograms, and a 700 Newton force was used to push it though, and the mu of k was 1.78. This time we placed the mass on a surface, obviously must have had some sort of different stuff on it, and it slid down a ramp with an angle of 25 degrees, and therefore the mu must have been 0.466. Oh boy, I'm pretty tired. Alright you guys, if you have any questions, then better show up to school like super early. I'll be here a little early. Anyway, have a good night, good luck, bye.